5G and network slicing. 5G supports multiple service verticals, which are very different in terms of expectations from network resources. To support these different service verticals, we need to divide our network. But there is one catch in this. The catch is, you can say, the great part is that these networks are actually implemented over a single physical network. So how do we really do it? The answer is network slicing. So in this particular session, we are going to talk about network slicing and what are the enablers in 5G that makes network slicing possible. So jumping back to our topic, 5G and network slicing. So there are quite a few important things we need to walk through in this. So first of all, I want you to understand what 5G is expected to do in the future. We then talk about some technology enablers in 5G because I want you to get feeling what is novel in 5G. Then we'll talk about network slicing. We'll talk about the motivation for network slicing. You know, why we are doing it, what's the objective, what does it do, what does it help with. So we'll see how a 5G network can help deliver network slicing. So we have basically two topics to cover here. First of all, we'll talk about why we need network slicing, and then we will explore what are the enablers for 5G or specifically for network slicing to make network slicing work. Okay, then let's leap into the network slicing. So network slicing. So this is the network slicing definition given by 3GPP. So what is network slicing? So network slicing is a mobile networking platform using which elastic and scalable access and connectivity related capabilities are provided as a service to customers in each geography using 3GPP standardized technology. Okay, so always remember these two words. One is elastic and one is scalable. So what is elastic or what is elasticity? So anything which has ability to grow or shrink dynamically, that thing we call elastic. Nowadays, most precious resources we have are spectrum and storage. So elasticity means we can expand or shrink our resources dynamically according to our needs. And the second important word you see here is scalable, or you can say scalability. So what is scalability? So scalability means to increase our capacity without impacting the performance of other resources or other slices or other users. So scalability means potential of a system to handle a growing amount of work. And how to handle more work? By adding resources to the system. This is called scalability. So you will understand these two words more clearly as we go along the webinar. At this moment, just remember these two words, elastic and scalable, as they will play an important role in the network slicing. A virtual machine host. The main purpose of operators is to reduce the capex and opex and earn maximum profit. For that, network slicing is excellent solution because here there is a concept of network sharing. The technology that lies at the core of network slicing is virtualization. The notion of network slicing is the virtual network architecture. It will enable powerful and flexible capabilities of creating multiple logical networks on the top of common physical infrastructure. So you can see here we have one physical server, or you can say we have one hardware resource. Then we have these virtual machines, right? At high level, you can say these are the four physical server logically. You can have, so you can see here we have four virtual machines. So if virtualization is not available, then what happens? We have to install four hardware resources. But with the help of virtualization, only one physical resource is enough. So virtualization basically lets you divide the hardware resources of a single physical server into the smaller logical networks, right? You can see here we have four smaller units or 4 logical networks. So you can see this physical server can host multiple virtual machines, and these virtual machines will run their own complete operating system, each with its own memory, storage, and network access. So in case of network slicing, we are dividing our physical resources into virtual machines end to end. It means every machine has its own RAN, own core, own transport, etc. Okay, so this is the virtual machine host. Little bit of background. So let's go little back in the past. I would like you to think for a moment about the existing wireless network that we have today, which is 4G LTE. 4G LTE is a fantastic network. It has provided us with much higher data rates as compared to 2G and 3G. It is an all IP network. It is great for doing things like accessing the internet and web browsing, streaming videos, doing all kind of social media, the stuff we do on the internet, and so on and so forth, and also doing VoLTE. But in LTE, we have one issue. It is a little bit of one size fit all scenarios. There is no way to differentiate various cases in LTE. Yes, we can differentiate traffic in LTE based on the quality of service, but when it comes down to every user who is connected in a cell on LTE, the RAN, the core, the transport, everything is shared between the users. So LTE is a shared resource. The network is shared. Not only that, all the users are in contention of same resources. So LTE is a bit of one size fits all. Now in 5G, that is going to change a lot. 5G has the promise of introducing lots of new diverse services. These services could be connection of many different IoT type devices, Internet of Things, smart home, smart cities, autonomous cars, sensor in the cars, sensors in all over the place for oil wells, electricity meters, smart variables, etc. All of these things are going to be new type of services that 5G will support. Secondly, with 5G, we will also be able to have a lot more and more varied business type models, right? A new type, you may have heard of this term, which is called MVNO, right? Which is Mobile Virtual Network Operator. So what is MVNO? So it is a wireless communication service provider that provides service to its customers. But the funny part is that it doesn't own any wireless infrastructure over which it provides service. So you can think how much money this MVNO can save. Then we have this business versus consumer, third-party services, or CSP services. So CSP is communication service provider. So as we start to get into this new range of services in 5G, we find one thing which is different from LTE or previous technologies. We find out that one size fit all scenario will not work with 5G, right? Because 5G has different use cases, different services, different business models, etc. We can't have contention of all the resources amongst all the users of these new type of services and application. So what's the solution for this? So the solution is network slicing. Network slicing is all about taking that one physical network end to end and dicing it up into the virtual slices. And with each slice being able to manage independently. With each slice maybe having dedicated resources that are not used in other slices. And with slice isolation, change in one slice will not affect change in other slice. This is the biggest benefit we have here as compared to previous technologies. Therefore, we can now optimize those slices to meet these very diverse requirements which are in 5G. So what is network slicing? Why slicing and why it is important in 5G? As I said earlier, 5G has very diverse requirement as compared to previous technologies 2G, 3G and 4G in terms of throughput, latency and reliability. The role of network slicing is to support these very diverse and extreme requirements for latency, throughput, capacity, reliability, etc. So the main purpose of network slicing is to create end-to-end logical networks, and all these networks should be isolated from each other. The main purpose is that they should be operated independently. So you can see here we have three different slices. One is tablets, one is mission critical devices, and the third one is IoT devices. So the tablet slice means independent RAN, independent core, independent transport, end to end, right? So it has independent logical RAN, logical transport, logical core, and logical cloud end to end. We'll see the details in a moment. So right now you can see we have only three slices, but there can be more slices in the future as well. But the point here is that these slices are completely isolated from each other, right? So with the help of network slicing, each scenario will be fully customized with network resources. And how these resources are allocated? They are allocated by use case or maybe subscriber type or application type from a common physical network. Okay, from a common physical network. Network slicing key feature in 5G. So you can see the concept of network slicing more on this slide. So network slicing offers an effective way to meet the requirements of a multitude of services and applications over a common network infrastructure, okay, over a common physical network, okay, over a common physical network. So it can be smartphones, it can be health IoT case, it can be mission critical devices, and so on. So clearly, network slicing is a key feature for the 5G system. It is all about transforming the network system from a static, one size fits all standard to a new standard. In this, logical network partitions are created, right? Logical partitions are created to serve particular purpose or to serve particular service or to serve particular customer as well. So in network slicing, a physical cellular network is divided into multiple virtual networks. And these virtual networks is called slice. And each slice is then used to serve the end user. Thus, network slicing will play a pivotal role in meeting these set of requirements for each user case. 4G versus 5G. So before jumping to more details of network slicing, we have to discuss few topics as they will act as a base for network slicing, or you can say foundation for network slicing. When the baseline 4G system is compared against the 5G requirements, improvements are required in different domains. There is no doubt that 5G radio or 5G hardware is more advanced as compared to previous technologies. But the most important thing that differentiates 5G is end-to-end flexibility. This end-to-end flexibility will come in large part from incorporation of software into every component. You may have heard of techniques like SDN, NFV, cloud computing. If we put all these together, it will provide lots of flexibility in 5G. And such flexibility will enable new capabilities in 5G, including the network slicing. So now if we look at this table, there are lots of differences in 4G versus 5G, like latency differences, download speeds, frequency channels, core. But I'm not going to discuss all of these things. I'm going to discuss here design for. Right? You can see here 4G is designed for mobile broadband services. But 5G has three different services at this moment. There can be many more in the future. So in this particular scenario, we are going to talk about these three different services, eMBB, URLLC, and mMTC, which are very different as compared to previous technology. Now, in case of eMBB, URLLC, and mMTC, what kind of services we are expecting? That we can talk about in our next slide. 5G uses three scenarios. So in this, we are going to look at the three uses scenarios of 5G. These user scenarios were developed by ITU, and these three cases are subsequently being adopted by 3GPP as three standard slices. Okay. For EMBB, URLLC and MMTC are our three standard slices. Okay. You can't change their numbers, and I will talk about various parameters soon. So for those three slices, everything is fixed. SST, slice differentiator, and many other parameters. Those parameters are fixed for those three slices. So let's talk about our first case. Our first case is EMBB, which is enhanced mobile broadband. So what's the function of this? So EMBB is intended to be able to provide the type of services that would typically use 4G for web browsing, video streaming, like ultra high definition, video calling, the type of traffic that often requires very high peak data rates. It may be not too much sensitive to latency, but is very bursty in the nature. So first use case here is EMBB, enhanced mobile broadband. It basically means more data to you as a consumer. If you may took around 3-4 minutes to download a movie before, well, hello. In case of 5G, you can do that in few seconds. So we see that as a very, very strong technical use case. As we see more and more data hungry applications coming out, the demand of mobile broadband will continue to increase, and which will lead to enhanced mobile broadband. As you know, in the end, operators are more concerned about seamless user experience. The second 5G case is ultra reliable low latency communication, or the URLLC. No idea who came up with this abbreviation. So URLLC is really about mission critical stuff that is new. That is, think of Ethernet cable being done wirelessly. So this use case has strict requirement for reliability, latency, and availability. Some examples for URLs can be industrial manufacturing, augmented reality, remote medical surgery, self-driving cars, etc. As you know, a certain types of application like self-driving cars, virtual reality, augmented reality, they have very strict requirements for latency and availability if you want to use them effectively and efficiently, right? So these applications require URLLC. So here we are trying to disrupt very heavy industries which are normally rely on totally different technology. So you see, URLLC is the second use scenario defined by 5G. And the third case is massive machine type communication, also called as MMTC. So this use case is characterized by very large number of connected devices. They typically transmit a relatively low volume of non-delay sensitive data, and devices are required to be of very low cost, maybe less than $5, and they must have very long battery life, maybe 10 years, 15 years, 20 years. So in case of MMTC, we are looking at a category of services where we need to connect a huge number of devices, for example, the Internet of Things. So a huge number of devices in a given area, but those devices may not necessarily need extremely high data rates or extremely low latency. Some examples can be smart homes, smart buildings, and smart cities. So these are the 5G technical use cases we are talking about. So think of it like a pyramid, and you can visualize all these three cases. So we have talked about EMBB, we have talked about MMTC, and we have talked about URLLC. And each of these cases have different requirements, which we can talk in next slide. But just remember, first of all, in 5G, as a standard, we have three cases. There may be many more cases in the future, but as a standard, we have only three cases: EMBB, MMTC, and URLC. And we have talked about some examples of all of these three cases as well. So as I said that in case of 5G, we have three cases, but each of these cases has different kinds of requirements as well, different kinds of, you can say, at high level parameters. So as we have talked that in 5G, we have three different cases, but to call any system 5G, we have some requirements. We have to fulfill those requirements. Only then we can call that system as 5G. So you can see here, the first requirement is MMTC, we have discussed that MMTC means we have large number of devices, deep penetration, and it should be power efficient and it should be of low cost. But how many devices should 5G should serve so that we can call any system 5G? So there should be 1 million devices or subscribers per square kilometers. If we are able to serve 1 million subscribers per square kilometer, only then we can call a system 5G. In case of LTE, if you remember, it was 100,000, right? So for MMTC, this is the requirement. It should be, we should able to serve 1 million subscribers per square kilometer. In addition to that, it should have high battery life and it should be of ultra low cost. Okay. So this is our first case, which is MMTC. The second case we have discussed is URLLC, which is ultra reliability and low latency communication, right? So, and we have discussed that what are the main features. First of all, it should be have low latency and it should be have high reliability. So what's the definition of low latency? How much latency we call it low? In case of 5G, we are talking about sub 1 millisecond. Okay. So latency should be at least less than 1 millisecond. Only then we can call any system 5G. Yes, there can be control plane and user plane. For that, we have different latency, but at high level, you should remember, we should have 1 millisecond latency. And what about reliability? Yes, reliability should be very high. If you're doing a remote operation, if doctor is doing a remote operation, if reliability is not there, how can a patient take this service, right? So reliability is, we call it 5 nines, we call it 99.999. So this should be reliability. Reliability should be 99.999%. Only then we call any network as a 5G. And the third case we have is EMBB, which is enhanced mobile broadband. And we have discussed in enhanced mobile broadband, we have high data rate, enhanced broadband. But how much data we call it high? So that should be 10 Gbps in the uplink and 20 Gbps in the downlink. Okay. So 20 Gbps in the downlink and 10 Gbps should be uplink. And at least 100 Mbps should be available everywhere, right? So 100 Mbps should be available everywhere. So these are the requirements to call any system as a 5G system. So now you have seen 3 use cases and each case has a very different requirements. Traditionally, if we have to implement these cases, we have to install 3 different physical networks, but not anymore, since now we have network slicing. So now the question comes, what do all these performance requirements for 5G means in terms of network slicing? How do those requirements tie into specific applications and services? So now in network slicing, as we see later, we are not limited to just 3 slices. There can be many more slices. But as you start to get looking into at network slicing, you are gonna come across a term called SST, slice service type. This is just simply a number that has been assigned by ITU to all standard SSTs or all standard slices. For example, for EMBB, my SST is equal to 1. For URLLC, my SST equal to 2. For MMTC, my SST equal to 3. So at some point, you may run across those SSTs. So you must know that from where these numbers are coming. So guys, we have seen 3 use cases in 5G. One is MMTC, one is EMBB, and the third one is URLLC. So in 5G, we have these 3 different use cases. These are completely different network requirements. So what we have, the network requirement for EMBB, the network requirement for URLLC, and the network requirement for MMTC are entirely different. But the challenge is that we have to run all these different services verticals on a single network infrastructure. So how do we really do it? How to achieve that? So to achieve that, we need to understand what we call is network slicing. We have to divide our network logically. So we have to divide our network logically, but based on a single physical infrastructure. So what the solution? The solution is network slicing. Now you have understand the purpose of network slicing. So now you must be thinking how to implement this network slicing technology. What are the things needed, or you can say, what are the enablers for network slicing, that we can discuss in next few minutes. To learn about network slicing, we have to see building blocks of 5G briefly. First of all, you can see in case of 5G, we have very large bandwidth, right? So in case of 5G, the bandwidth can go up to 400 megahertz for high band, or you can say millimeter waves, right? So it can go up to 400 megahertz. As you know that according to Shannon laws, capacity is equal to bandwidth log 1 plus sin r, right? So if our bandwidth is high, our capacity will be high. So in case of 5G, we have very high large bandwidth, and we have very diverse spectrum. We have low band, we have mid band, we have high band. In addition to that, other building block is called beamforming or massive MIMO. So beamforming is successful only when we have large number of antennas. As you know, or as the wavelength increases, the size of antenna shrinks. More the larger the wavelength, lesser the size of the antenna. So in case of beamforming, we need large number of antennas. So it is not possible in the low band, because if we do beamforming in the low band, the antenna size may be many meters big, right? But with the help of beamforming, we can take the advantage of this high band and we can improve our signer. And as I said earlier, higher the signer, higher the capacity. So with the help of this beamforming and massive MIMO, we can drastically increase our signer, and which in turn can improve the capacity. Also in 5G new radio, we have a flexible frame structure. If you remember, in case of LTE, our subcarrier spacing is fixed, which is 15 kilohertz, but not anymore in 5G, because in 5G, we have flexible frame structure. We may have 15 kilohertz subspacing, we have 30 kilohertz, we have 60 kilohertz, we have 120 and 240. So depending on the low band, high band, mid band, depending on the services, depending on the use case, our subcarrier spacing can be allocated. So also, in addition to these things, we have flexible subcarrier spacing in 5G. Okay. Then we have this split architecture, right? So 5G has been divided into CU and DU, right? So DU is distributed unit and CU is central unit. So with the help of DU, distributed unit, it generally is at the site or near to the site. It is implemented at the lower layers of the air interface protocol stack, and those conditions are very time sensitive. The other component is this, which is called central unit. The central unit implements the upper layers of the protocol stack. The split architecture means that we can now put this central unit and this distributed unit at different locations, right? You don't have to combine them. We can put central unit in the common hub, which can support multiple distributed units. Okay, and the CU can be implemented using virtualization on a cloud platforms, and this will again provide flexibility and scalability. On the core side also, we have this cloud-based core, and many things are there. Okay, so guys, these are the basic enablers in case of 5G. We have discussed cloud native, massive MIMO, millimeter waves, all of these. So all of these things, or all of these parameters, all of these things, conditions makes 5G a very flexible and scalable system. You can see slicing is one of the part which can make 5G possible. So now we have to talk about what are the enablers of slicing. What are the main enablers of slicing out of these enablers, right? So let's talk about main enablers of slicing. So network slicing enabler. So the first enabler we have to talk about is spectrum. So 5G provides us with much wider array of spectrum that is available. Mainly it is divided into two frequency ranges. One is FR1 and one is FR2. As you know, as you can see that FR1 is for low band or mid band, and FR2 is for high band or millimeter waves. The main purpose of FR1 is to improve the coverage. The main purpose of FR2 is to improve the capacity, right? So being able to take advantage of those different pieces of spectrum is one of the enablers for network slicing. Then we have this user subscription data. In LTE, we provided in the subscription data a list of PDNs or APNs, access point names that a subscriber could access. But in 5G terminology, the term used for that is called DNN, or you can say data network name. So now what happens in 5G, we allocate for a subscriber a specific data network to a network slice type. So when the user wishes to connect to that service, they are going to assign to a specific slice type. And we have this SDN, which is software defined network. So traditionally what happens, networking devices were designed to perform a set of functionalities. Vendors need to update the design or change the hardware to enable the new features, but not anymore. In case of SDN, control and user planes are separated. So any change in the control plane will not impact the data plane, and any change in the data plane will not impact the control plane. So SDN allows the separation of control functionalities from the data transmission network. So there are many new concepts in 5G, but personally, I feel separation of control plane and user plane make 5G different from other technologies. So SDN enables easier management of the large scale networks by decoupling the control plane from the data plane. Then we have this NFV, which is network functional virtualization. So while SDN covers the revolution of routers and switches in the network, but NFV handles other boxes in the network that performs more complex packet processing. In a traditional network, we have various network functions like router, switch, firewall, etc. But not anymore, because now we have NFV, which is network functional virtualization. So network functional virtualization calls the virtualization of network functions, which are currently provided by middle boxes, firewalls, and gateways. So using virtualization and cloud technologies, NFV allows legacy NFVs supported by various equipment to run on the software, not on the hardware. So in 5G, core will be implemented as a virtualized network function. The main purpose is again to support network slicing. The last enabler we have is core, or you can say cloud enabled core. First of all, let's see how a traditional IT infrastructure was developed in the corporate networks. So first we have infrastructure. So typically all physical infrastructure like servers, which includes processors, compute, storage, and network components, they were actually deployed in the corporate network. On the top of this, we have this platforms. So platforms are typically the runtime environments, operating systems, etc. And all these services were deployed and provided by the servers which were available in the corporate network. Now, everything should be on the corporate network, maybe in the building or maybe in some factory, right? But it can take lots of your space, lot of your power, lots of your energy. However, nowadays, there is a one thing comes called cloud. So nowadays, all these things, whether it is infrastructure, whether it is platform, whether it is services, all these things can be stored in something called cloud. And this cloud infrastructure is available over internet. So anybody sitting anywhere in the world can access this cloud infrastructure and can do the configuration of resources. Now you can access these devices from any mobile phone, any computer, or any laptop, or any desktop, right? You can see here we have three type of delivery models, like IaaS, which is infrastructure as a service. Then we have PaaS, which is platform as a service, and SaaS, which is software as a service. So these are the 5 enablers in case of network slicing we have talked about. One is spectrum, one is user subscription data, third one is software defined networking, fourth one is network function virtualization, and the fifth one is next generation core. Okay, so these are the 5 enablers in case of network slicing. So this is a definition we have seen for the network slicing earlier. Okay, so let's go on and to look at the network slicing through this slide. So first of all, in terms of devices, and remember now we are talking about devices in 5G. We are not just talking about traditional consumer smartphones. but the type of devices that, for example, device that require high data rates like EMBB, right? Like 3D or ultra high definition, or vehicle to vehicle communication, or vehicle to everything communication, or the type of slices for IoT type devices, Internet of Things, smart variables, transceiver meters, point of sale machines, right? And so on and so forth. So these could be examples of different services types of which an operator may want to provide network slicing. So in order to provide this service, we are going to dice up the network around slice. Of course, managing different slices for these different types of services as well. So 5G network slices. All right. So again, some kind of type of slices. So here we show a number of different types of devices. First one you can see here is the smart car, right? Autonomous car. It would access the automotive slice. The automotive slice may provide service like advanced traffic navigation system, vehicle to vehicle communication, or whatever it might be. Then we have this electrical utility slice. So utility meters are put in the electrical utility slice. The quantity of these meters can go from 1,000 to millions, but they require pretty low data rates and pretty infrequent data transmission. So we can support a lot of them. And then we have this consumer slice. So it is for broadband type services and those types of things. Also, we have discussed there are three main cases in case of 5G. One is EMBB, one is URLLC, and one is MMTC or MIOT. And I already gave you that for EMBB, SST is equal to 1, for URLLC, SST equal to 2, for MMTC, SST equal to 3. So those three standard slices means we can support roaming between operator networks because those slices are standardized. But an operator may define their own slices as well. These would be unique to a specific operation, but will not be able to roam using those standard slices. So here you see two parameters. One is SST and one is SD, which is slice differentiator. So SST, you know, is slice service type, but the second parameter here is slice differentiator. So what is this slice differentiator? So in network slicing, the slice differentiator is directly related to SST. So slice differentiator is used as an additional differentiator if multiple network slices carries the same SST values. For example, take the example of EMBB, right? The SST of EMBB is 1, right? But under EMBB, we may have different services, or you can say different sub slices, right? So you can see here in picture, we have two services. One is broadband gold and one is broadband silver, and they have the same SST. But how to differentiate between broadband gold and silver? For that, we need this thing which is called slice differentiator, right? Now the question comes, how many slices are possible? There can't be unlimited slices, right? There can't be unlimited slices. So let's see how many slices are possible. You can see here for SST, we have 8 bits. For SD, we have 24 bits. So you can see here, the number can go very high. So 2 raised to power 32 slices are possible. This is roughly around 4 billion. And you can see that, you can visualize that this is such a big number. So we can have different kind of slices according to our needs, and slices can be standard or non-standard. Okay. So as I mentioned earlier that network slicing is end-to-end. So whenever we put a slice in place, there is going to be slice for RAN, there should be slice for core, and there should be slice for management slice, right? So what it means if I allocate a number of network functions and a piece of the RAN, a piece of transport, a piece of the core, they should work independently, right? So this is the main function. And you can see here one thing called MANO, which is management and network orchestration, and it plays a very important role in the management. So you can say network slicing is all about providing stable end-to-end quality of service and optimize the resource sharing. We have talked about 3 standard slices. We have talked about EMBB. We have talked about URLLC. We have talked about MMTC, right? And now One of the very important characteristics about network slicing, it is end-to-end capability in the network. It is end-to-end from device through the air interface, through the G node B, through the backhaul transport networks, through the core network, and to the management system. It is end-to-end capability, 5G RAN, 5G core, 5G network, end-to-end. So in order to put a slice in place in network, we will slice the RAN, we will slice the transport, we will slice the core, we will slice the management system as well. So as you can see the graphic here, you can think like this. Previously, we have one fruit and we are bound to eat slices of the same fruit. But now, in case of network slicing, slices of multiple fruits, each of which their own characteristics is possible, right? So what's the takeaway from this webinar? So you can see, so if you want to take some takeaway, these are 5-6 points we should take away. That first of all, network slicing run on a physical network, but it is divided into various virtual networks. So you do not need a new hardware for a new service. Then optimizes uses of network for each intended user scenario. So all the resources are efficiently utilized according to need, according to priority, according to quality of services. Uses a set of access and core network functions. So now we are taking the advantage of cloud and NFV technology so that 5G core can be virtualized, is controlled and managed independently. So with the help of SDN, we are dividing data and control plane so that both planes can be managed independently, create on demand. So all the logical networks will be created on demand and unutilized resources can be utilized somewhere else. Does not interfere with other functions and services on coexisting slices. So since slices are fully isolated from each other, so performance of one logical network or use case will not affect any other network. So guys, long story short, network slicing is an emerging trend that seeks to transfer a network designing, planning, implementation through software programming. So you can say network slicing is the real need of today. With the growing development of 5G and the cloud architecture, the technology is on the brink of development or deployment. So network slicing provides necessary flexibility and modularity to create logical networks through NFV, which is network function virtualization, and SDN, which is software defined network and cloud computing. So this is all about network slicing.